Okay, so let's get started with parallel programming with OpenMP. Before we get into the actual OpenMP and the syntaxes of the OpenMP, let's get started off with shared memory programming model, what it is and what are the advantages and disadvantages of shared memory model. Okay, how it works. Okay, so why we want to use shared memory programming model. Okay, so if you look at today's processor, they are all multi-core CPUs, right? So whether it's a laptop based processor, server based processor, or even our mobile phones, whatever processor we have, those are all shared memory based programming models. Okay, because they use multi-core CPUs, which are essentially connecting to the same memory locations. That is, the same RAM is being used for all these multiple cores on the same processor. Okay, so now what you can do is you can have multiple threads. Okay, reading writing to the same common variables. Okay, directly into the same RAM. Okay, so we don't have to explicitly send and receive the messages here, simply because now everybody has to just go and read write to that particular location, and everybody else will be able to see the updates made to those common variables because they are shared. Okay, so why we want to learn this, mainly because this is the simplest possible parallel programming model to begin with. Okay, and OpenMP is the standard API in this particular model. Okay, it's been around for quite some time, and people have been using it extensively across a lot of the scientific applications and all the other types of applications. Okay, so in short, what is shared memory? Okay, so it has a one address space and many threads trying to read write to some common variables. Okay, and trying to communicate with each other via this common variables. Okay, so what is this model? Okay, in simple language, what we have here is we have one process with multiple threads, and they have the same global data that they can actually read and write and access to. Okay, so here the communication is simply that you just go and read write to the shared variables, and every other threads will be able to see it. Okay, so and as because we are not sending and receiving the data between the threads or the processes. Okay, it's just plain vanilla memory access. Okay, and that's why it's very fast, because there is no sending and receiving the message over some kind of a physical network. Okay, so it's fast, but because now that everybody can read write to the same memory location, we have certain challenges that we'll discuss in the following slide as well as following lectures. Yeah, so what we have is we need some kind of coordination when multiple threads are reading writing to the same memory location. That's the key challenge here. Okay, and by default all these things are generally shared. Okay, certainly every thread may have their own private memory locations, but good amount of data will be declared as shared, and if you don't specify, it's generally default, it's shared. Okay, so all the guys can just go and access that particular data. Okay, read the data as well as write to that particular data. Okay, so how do these threads communicate in shared memory programming language? Okay, so what you have is, let's say thread A writes to a shared variable. Okay, now without communicating that update, okay, some other threads can just come and try to read that particular value, and they will see whatever latest updates, whatever thread A has made to that variable, directly visible into the same variable by other threads. So for example, thread B comes and tries to read that value, it will see the value updated by the A. Okay, so it's same variable, multiple threads are trying to read it. Okay, so here we don't have any special function calls, or there are no sends or receives involved. What you do is you just go and modify the value, everybody else will be able to see the latest value. Okay, so in theory it seems very simple. Okay, but the order in which this operation happen is also very important. Okay, so if multiple threads are trying to access the same memory location, okay, especially when they want to write to that particular memory location, then we have a problem. Okay, so if multiple threads are just reading from the given location, then that's okay, but at least two or more threads are trying to write to that same memory location or the same variable, we have a challenge. Okay, why? Okay, because multiple threads might modify the same value at the same time, okay, or try to modify the value at the same time, then we will have an issue. Okay, so typically we refer it as a race condition, okay, or the data race. Okay, so to solve this problem, there are multiple tools to coordinate among the multiple threads. So you have locks, barriers, atomic operations, or reductions. Okay, so we can use these tools to solve such issue. Okay, so in summary, okay, shared memory is very fast, but you have to be very careful when you are writing such codes on shared memory machines. Okay. Okay, so what is the problem here? So as you can see, uh, you have a variable called as sum, and both these threads are trying to increment that value using their own sum value. Okay, so the challenge here is if that incrementation or writing of that particular value happens at the same time, we have an issue. Okay, why? Let's see. Okay, so when both wants to update that particular value, what will happen is both will go try to read the old value, because now both are trying to simultaneously update the value. Okay, both will read the initial value as say 10. Okay, as the image depicts. Okay, now first thread tries to increment it by 1, so it's supposed to write that value as 11. Okay, and the second thread tries to increment by 2. Okay, so it's supposed to write back the value as 12. Okay, so one thread wants to increment by 1, another thread wants to increment by 2. Okay, so what should be the ideal answer? The ideal answer should be increment by 1 and then increment by 2 is essentially increment by 3. Okay, so answer should be sum is equal to 30. Okay, once both these guys have written their values. But because now both the guys have read the original value as a 10, okay, they are going to write either 11 or 12. Okay, one is incrementing by 1, another guy is incrementing by 2. Okay, so the answer would be either 11 or 12 and not the correct answer, which is 13. Okay, what is the problem here? Because it depends on who writes the value first, that thread's value will be overwritten by the another thread. Okay, so because whoever finishes the second, his value will be reflected every time when I run the same code again and again. Okay, every time I will not be able to see the same exact value. Okay, sometimes thread 1 will be able to write at the end, sometimes thread 2 will be able to write at the end. Okay, whoever writes at the end, that fellow's value will be reflected in the sum value. But as we discussed, both these values are wrong. The actual sum should be 13, but still either these guys will write 11 or 12. Okay, so this is one of the key bug in or the issue in shared memory programming. Okay, certainly every shared memory programming model has some solution to it. As we discussed, locks and barriers and whatnot. So those coordination tools are already available. Okay, so OpenMP also has this different tools to prevent such scenarios from happening. Okay. Okay, so coming to the OpenMP. So in this whole context, where do the OpenMP fits? Okay, so OpenMP earlier, as people used to refer as a open multiprocessing. Okay, so it's been an industry standard since 1997. Currently, okay, the latest specs are 5.2 or depending upon when you are watching this video. Okay, so what OpenMP offers is it offers different compiler directives, which we will discuss in detail in following slides. Okay, and it provides a runtime library of different function calls, and plus there are certain environment variables which you can actually set while running the code, okay, through command line, okay, or the terminal. So OpenMP supports C, C++, Fortran natively. Okay, and many of these compilers such as GCC, Clang, Intel, Microsoft Visual Studio, and all these compilers support, and many more actually support OpenMP. Okay, so on GCC, how do we compile? Okay, so this is the compilation flag GCC space -f OpenMP, and then you specify whatever file name you have. Okay, so it will compile that particular given code using OpenMP. Okay, so in summary, what is OpenMP? Essentially, OpenMP is nothing but a bunch of pragmas that take your serial code and convert it into parallel C code. Okay, without really modifying like URC code significantly. Okay, so what is the difference between the shared memory and message passing? So we are going to talk about OpenMP under shared memory paradigm, and we are going to talk about message passing, that is like MPI under message passing paradigm. Okay, so in shared memory we create threads, okay, multiple threads in a single process, whereas in MPI we have multiple processes, okay, which run in parallel. Okay, in shared memory, the communication happens through the way of reading, writing to shared variables, whereas in MPA or the message passing, we explicitly send and receive the messages between the different processes. Okay, the hardware essentially for shared memory is generally a multi-core node or multi-core system where you have a common memory pool and you just go and access that particular memory location. Okay, whereas in MPI, okay, you can run MPA on a single multi-core processor, okay, or cluster of nodes. Okay, so you can have a bunch of servers connected together with high bandwidth network, and they can communicate with each other via some like gigabit Ethernet or InfiniBand or some network. Okay, from the complexity point of view, shared memory programming is very easy to start or understand. Okay, so you can quickly start writing your codes using OpenMP, whereas MPI is or message passing is slightly more complex, and you have to deal with the parallel programming or distribution of work a little more attentively with respect to how do you distribute the work and whatnot. Okay, so slightly more complex than what shared memory programming provides. Okay, scalability point of view, certainly due to cost and efficiency and other factors, you cannot have really large number of such multi cores connected to a same common memory pool, whereas because in case of message passing, because they are connected via network, you can have really thousands of nodes connected to each other via some kind of a network, high speed network, and you can write the code which will scale across all these number of nodes. Okay, so scalability wise, message passing is much more scalable. Okay, whereas OpenMP is has a limited scalability due to the complexity of system design. Okay, where you have large number of nodes connected to the common memory pool. Right, so I'll just give you a simple code snippet, and I'll show you demo also. Okay, so you can see here we have a very simple code where we have written this hash pragma OMP parallel, okay, which we'll discuss in following slides. But what this thing does here is, okay, this particular block of code essentially will run in parallel using multiple threads. Okay, so what we have is we have a array called as data, which contains 4 values, and now for this particular code we declare a variable called as id, and we will get a unique identification number for each and every thread, and we will just print, okay, what that thread is and what value it's trying to read. Okay, I'll show you the detailed loop. Okay, so in this case, as you can see, data is a shared variable. Okay, it's an array, but it's a shared array, so all the threads can access each one of these values, whether it's 10, 20, 30, 40, all these values are accessible to all the threads. Okay, whereas because we declared id inside this particular block, okay, id is private, and each thread it's going get its own id, okay, provided by the OpenMP runtime. Okay, and it's a unique identification for each and every thread. Okay, and as you can see, we are not sending and receiving any messages here. Okay, so or we are not making multiple copies of the same array for each and every thread and whatnot. Okay, so let's quickly try to see the actual code, and I'll just compile and run it for you, and we will have a detailed discussion on these codes later when we come to all these pragmas and all. Okay, so we can see that we have included this hash pragma OMP, sorry, we have declared this omp.h as a header, and here I use hash pragma OMP parallel. I added additional clause here, which we'll discuss again in the following lectures. Okay, so what this says is I want to create 8 number of threads. Okay, that's what it essentially says. So we have this array which is a shared array. Okay, we will by default this will be shared whenever we are inside a parallel region. Okay, So this is called as a parallel region because we have written this hash program in parallel, and this particular block of the code will be executed by each and every thread. Okay, here we are creating 8 threads. So all the 8 threads will run this thing in parallel, independent of each other. Okay, even though they are trying to access the same memory location. Okay, which everybody can just go and read write to. Okay, so what we will do is we declared a variable called as TID, which is private variable because the scope of this variable is within this block. Okay, we said okay, so get me the thread num. Okay, so OpenMP is going to get you a unique ID. Okay, for your thread, and what we'll do is we'll print. Okay, a certain thread is trying to access array of that thread's index, and it will print the actual value of that particular index. So if my thread number is 4, okay, so 4 is this guy. So essentially in OpenMP the indexing starts, or in C indexing starts from 0. Okay, so this guy is the 0, 1, 2, 3, 4. Okay, so if my thread ID is 4, okay, it will print thread 4 sees array of 4 is equal to 50. Okay, that's how it's going to print it. Okay, so we are going to discuss this thing in detail, but just to give you a flavor of it, we have a small demo here. Okay, so let me compile and run this code. So the compilation command is gcc -f openmp. Okay, then we'll say the name of the file, which is okay, what is the name of the file? Shared model.c. Shared model.c. Okay, code is compiled. I'll just run using a.out. Okay, so you can see thread 2 sees array of 2, which is 30, thread 7 sees array of 7, which is 80, and so on and so forth. Okay, so depending upon the thread number, it sees a different value or prints the value. All the threads have all these values accessible, whether for reading or the writing, it doesn't matter, but all these values are accessible. Okay, it's just that in this particular code we are just that thread 0 is accessing only 0th value, 4th accessing 4th value, and so on. Okay, so another point to note here is you can see if I run this multiple times. Okay, so every time the order in which the threads are getting executed is not same. Okay, so which we'll discuss in following slides, but that's an important point to note here. Okay, so we'll stop here and we'll continue with the next section.